All right, looks like we are live. Welcome to Standing for Truth. My name is Donnie B, and I am your host for today's important program. I also have my co-host George Bond here with me as well. Thank you, everybody, for joining. It is a privilege to once again have Michael J. Oard back with us for a presentation and discussion on ocean sediments and incredible new flood developments. We will also, as usual, be taking audience questions after Mike's presentation. So please make sure to tag either myself or my co-host, George Bond, with your questions, and that way we won't miss them. Mike has been here on the program many times before. Actually, this is Mike's 8th time here. And all of his previous presentations are linked in the description box. You will find presentations and talks on the receding floodwaters, the Ice Age, answering challenges to the global flood, refuting more objections to flood geology, the Green River Formation, the Grand Canyon, and a presentation and talk on mammoths. So please do check those out, as they are all must-watch programs. Now, before I hand it over to Mike, I do want to give our guest a quick biography here, introduction. And so Michael has a master's science degree in atmospheric science from the University of Washington and is now retired after working as a meteorologist with the U.S. National Weather Service for 30 years. He has researched and speaks on the compelling evidence for Noah's flood and the ice age that followed, and how the incredible woolly mammoth connects to biblical history. Michael has published many papers in his field and is widely recognized and in widely recognized journals, and has written An Ice Age Caused by the Genesis Flood, Ancient Ice Ages, or Gigantic Submarine Landslides, the Missoula Flood Controversy, and the Genesis Flood and the Frozen Record. He is also author of Frozen in Time, The Weather Book, and Life in the Great Ice Age. You can also find more information from Mike on his website and also on the creation.com website, which is linked in the description box as well. Mike, thank you so much for giving us your time for today's program.
Oh, you're welcome.
And George.
Anyway,
Yes, good morning. Sorry, I was distracted by the chat. Someone wants to ask me a question. So, okay.
Okay.
Mike, I'm suffering some hearing loss. I went to the doctor the other day and I said, Doc, I think my hearing's going. He said, what are the symptoms? I said, he's a big fat guy and his wife has blue hair.
What are the Simpsons? Is that the question you thought?
Yeah, he asked me, what are the symptoms? And I said, it's a fat guy and his wife has blue hair. Come on, Simpsons.
Yeah.
Oh, I don't watch that. I've never watched it. So.
So let me hand it over to Mike. Mike, how you been? And a little bit about yourself before we get into the presentation.
Okay, well, I've been researching almost 50 years in this topic. Ice Age, the flood, dinosaurs, mammoths, global warming, a lot of things in earth science. The floods on Mars just recently, and just lots of things I come across. I try to keep up with about 50 earth science journals, go through the table of contents, find a good article that's related and copy it, read it. So that's how I find all kinds of new information for those great perspective articles that you can get in the Journal of Creation. So this research project started by reading the results of the amount of sediments in the ocean. For a flood model, which many of us are working on, and make it more sophisticated. It helps to know where the sediments are and how they got there. So this was a new research report on the ocean sediments. And that really, between three of us, John Reed and Peter Kleberg and myself, we realized we have a gold mine determining how they got there and what they mean for the early flood. And what they would imply for the flood model. And so that's what this talk is about. And so we want to know the global sediment distribution, not only what's in the ocean, but the continent. So because this research project called GlobeSed, it was just for the oceans, and they divided it right at the shoreline. So yeah, the oceans and the continents. And I will be dealing with the bulk sediments, both in the oceans and the continents. And I'll have no regard for the geological column or the ages, but I'll have a comment about the Cenozoic at the end. I will not discuss mega sequences. We don't know what the influence would be there. And we'll deduce the origin and meaning of the ocean sediments first. And we're working on the continental sediments, as I'll explain why we're doing that. Anyway, this GlobeSed project has had 3 estimates of the global ocean sediments, mostly from seismic reflection and drilling. And each iteration, like I said, 3 iterations. The third one was published by Strami et al. 2019 in the journal called G-Cubed. That's kind of a shorthand for the journal called Geochemistry, Geophysics, and Geosystems, published by the American Geophysical Union. And the estimates look pretty accurate now because they found sediments, or they didn't find them, they were there, but they probed them in places that were very difficult to probe before, like the Arctic Ocean and off Antarctica. And some of these sediments are so deep that they've made estimates in the first 2 iterations that were not that good, but now they got the depth of these sediments. So they look pretty accurate. And here's the map from that project. And you can see the scale on the left. The blues are shallow. You can see practically all the deep ocean has hardly any sediments. Then when you get up into the green area, you're getting towards 10,000 meters. And you can see where the green area is along the edges of the continents off of most of them and in the Mediterranean Sea. And you get up into the red, you're getting up to over 1,500 meters of sediment. And you can see some red areas there. In the Arctic Ocean has a huge amount of sediments, mainly on the continental margin. Also the Gulf of Mexico, off the eastern United States, the Bay of Bengal, and in the Weddell Sea in Antarctica, which is down in here, if you can see my cursor. So they're along the margins. And it's huge. And we've been able to do cross sections across this sediment. First of all, I'm going to talk about this cross section across the Atlantic. And you can see the deep troughs off the east coast of the United States going down about 1,500 meters, and off of Africa, 1,500 meters. Hardly any sediments in the middle. That line below the bathymetry and topography is the depth of the Moho, which is rather shallow in the oceans, but deepens over the continents. But you can see the continental shelf. Like here, it's really flat, and then here's the slope, the continental rise, and it's above this deep trough of sediments off the eastern United States. And we even have smaller cross sections, which I'll show you soon. But anyway, these are the ocean sediments. The total on the left is the province. They divide the oceans up into 3 areas: the continental margins, the deep ocean, and the transition between the margin to the deep ocean. And there's the area in that second column to the 10 to the 6 square kilometers of the ocean, of where the sediments lie, and then the sediment volume, 10 to the 6th power cubic kilometers, and then the mean thickness. So for all the oceans, the mean thickness of sediments is 927 meters. Along the continental margins, the average is about 3,044 meters. Transition zone, 2,189, and the deep ocean, 404 meters. So that's where the sediments were. That's their volume. So what's the meaning of all that? Well, we're going to go into that. First of all, some cross sections. Here's 3 cross sections across the Gulf of Mexico, off Georgia, and up off New Jersey through the margin sediments. And you can see the color code there. The blue is now about 1,500 meters, and even down to 20,000 meters is in the red areas. So here's the cross section across the Gulf of Mexico. And the shoreline is this vertical line right here. So the cross section starts well up into Texas. And the Gulf area has collected a lot of sediments that just continue to deepen down into the Gulf of Mexico. Right in his brown area, over 15,000 meters. And here's the Yucatan Peninsula right in here. So that's the volume in the Gulf of Mexico. Now, off Georgia, here's the volume. Here's the shoreline, that vertical line there. And here's the deep trough right off the coast. But we have a plateau called the Blake Plateau that's a little different than on the continental shelf before you drop into the deep ocean. And here's a cross section over that area right there. The flat shelf, the continental shelf, is very flat. It deepens slowly out into the ocean. It goes out hundreds of kilometers in some areas, and then suddenly a drop off. It's a real unusual profile, which I'll comment on here soon. Anyway, this goes across the Blake Plateau, which I don't know the origin of that, and then finally into the deep ocean right there. And then here's the cross section off of New Jersey. Lots of sediments in New Jersey. Here's the shoreline right here. And then here's deep trough. It's called the Baltimore Canyon. It parallels the coast. And that's where the continental shelves have deposited. And then you have the continental slope that just is a sudden drop off, and then a gradual sinking or falling down to the deep abyssal sea bottoms. That's called the continental rise right there. So what is the origin of this sediment? Well, we went into all the possibilities, which I'm not going to give you the details, which will be published in the Creation Research Society Quarterly. First of all, we can eliminate pre-flood sediments and early flood sediments. They're not. And the only other options are late flood runoff and the post-flood. And the post-flood, there's 2 options. Post-flood catastrophes, for those creation scientists that believe the Cenozoic is post-flood. To account for the Cenozoic, you'd have to have monstrous post-flood catastrophes. And then you have normal post-flood inputs, like river inputs and other things. And I'm going to focus in on a little more on the bottom 2 there. No post-flood catastrophes. Why? Well, first of all, let's look at the time divisions of the geological column. We're going to assume the geological column for purposes of discussion. I believe in a general order of the geological column, but with areas that are that could be out of sequence. Anyway, this arrow right here is where people who believe the Cenozoic is post-flood place the flood post-flood boundary at what's called the KT boundary, the Cretaceous Tertiary boundary, or KPG boundary. PG standing for Paleogene. And so they'd have to account for all these sediments being post-flood. And this is the other option, the late Cenozoic option, especially at the Pleistocene boundary. But I don't take those boundaries as precise. I sometimes think the boundaries in the Miocene, sometimes in the Pliocene, and sometimes even in the early Pleistocene. These are just utilitarian designations. And in every area which must be evaluated on its own merit, it can vary because of the way they define things. And even the post-flood sediments can be in the Oligocene in some areas. Like I believe the Australian marsupials, examining those areas, they look like they're post-flood, and they date them clear down to the late Oligocene. But it's interesting. I researched that and published 2 articles on it in the latest Journal of Creation, and discovered that in the early 1900s, they dated all those marsupial fossils as Pleistocene. Well, that makes sense. Pleistocene, post-flood in general. But then they got to seeing, oh, here's a primitive feature. It must be older. And they kept doing this and doing it and pushing it down to older and older based on little tiny glitches in the bones in various organisms. And so that's how they pushed it all the way down to the late Oligocene. And they essentially date these areas by the stage of evolution. Yeah, the stage of evolution is a dating method, especially for the Australian marsupials, and in some cases in South America and North America. I didn't mean to get off on that tangent, but I did. But anyway, the reason I believe that the post-flood boundary is up here is these 33 criterion. And you can get these on my website. I have a whole ebook on this topic. Also, they were published in the Journal of Creation. To the right, you can see the references where they were published. And I'll just pick one. Thick, pure coal seams in the Cenozoic. Like in the southeast Montana and northeast Wyoming, we have some layers up to 200 feet thick of almost pure coal that's dated early Cenozoic. How can that be post-flood? And there's coal seams in other areas of the world up to the Miocene. So coal indicates that you have a high boundary. And same with all these other ones. I rated the strength based on whether I thought those who believed in a KPG boundary could explain it or not. And I think in the indicate strong as they can't. And possibly in the weak they could. There's not very many weak ones. Geomorphology is just one piece of evidence. Sedimentary rock thickness, Cenozoic sediments. There's some. They have the thickest sediments of any period of the geological column. They're very thick. In some places, they're over 10,000 meters thick. And how can they be post-flood? I'll ask. For instance, in the South Caspian Basin, over 10,000 meters of Cenozoic sediments, mainly Pliocene and Pleistocene, I might add. Anyway, these are 33 reasons why I put the high flood boundary. Therefore, there are no post-flood catastrophes to add ocean sediments on what was deposited during flood runoff. And then we have uniformitarian post-flood options, and they're all small. For instance, transport by rivers in 4,500 years since the flood, assuming the Masoretic text, if you believe in the Septuagint, the end of the flood was about 5,300 years, I believe, something of that order, years ago. And anyway, you'd add maybe about a quarter of a meter in that amount of time of sediments to the ocean. Hardly any. Even if you add the ice age with higher sedimentation, it's not going to mean anything. And wind, ice, and volcanism are even less than the rivers. And there's coastal erosion, which they thought was only 2 to 4% of the total erosion from the continents going into the ocean, until they did a research project in Europe and discovered that it's about 33% of the river erosion. So I'm going to end up writing an article maybe this winter about that. And so, but that's still small. They're both small. So the upshot of it is practically all the sediment along the margin is from the flood. This continental margin, the transitional zone from the margin of the deep sea, all this sediment is from flood runoff. Then the deep sea ocean, there's where we get into some issues, which I will talk about next. So if you add up the volume of all the margin and near margin sediments, 2.24 times 10 to the 8th cubic kilometers, the area of the continent is 1.49 times 10 to the 8th cubic square kilometers. Dividing into that, you get an average depth of 1,500 meters for all the margin. But what about the deep ocean sediment? Well, sedimentation in the deep ocean today is very slow. Maybe about 1 inch every 4,000 years. But during the Ice Age, you'd have great overturning of the ocean because you started with a warm ocean. It cools from the top down, cool air, denser, and it sinks in the ocean. And you get the warmer water rising and getting caught in the ocean circulation. So you'd have a great overturning of the ocean in the Ice Age. And the significance of this is that in the upwelling part, you get huge amount of chemicals that microorganisms need, like phosphorus, silicon, and therefore you're going to have huge blooms of microorganisms during the Ice Age, huge blooms. So much so that you're going to, when they die, their skeletons end up on the bottom of the ocean, you're going to have rapid sedimentation during the Ice Age on the ocean bottom. How much? I don't know, because we know that there would be flood input to the deep ocean, mainly in the form of clays. So the way I figured this is if none of the sediments are from the flood out in the deep ocean, that means the depth eroded from the continents is 1,500 meters. The amount of flood runoff would be 1,500 meters since the peak of the flood, approximately day 150. Then you can see the other subdivisions, 25%, 50. So what I did is I split it right down the middle because I don't know. There's no creation scientist has done any significant research on ocean bottom sediments. And so when I add half of the deep ocean sediments to the volume on the margin, it comes out to about 1,900 meters of ocean sediments are from flood runoff. 1,900 meters, that's huge. And that's telling us a lot about the flood in general. So in conclusions from that, practically all margin sediments are from flood runoff, about 50% of the deep ocean sediments from the flood. And if we place that sediment back on the continents at the peak of the flood, about day 150, the average continental erosion, you'd add that 1,900 meters to what is left. So that's what we'll do. This is kind of a block diagram of that. Here's the current continental surface. This is just a schematic to show a principle. And during the recessive stage of the flood, which late Roy Holt called the Erosiozoic, to kind of have it jive with the Paleozoic and all those zoics in the uniformitarian geological column. So that was much eroded down since day 150. Then how much is left? And that would give us a total amount of sediment at the peak of the flood, which is a very interesting number. So there's been scientists that have been trying to estimate the current continental sedimentary rocks. Oh, and by the way, I need to back up. 1,900 meters might seem like a huge amount to people. That's about 5,000 feet. But I've done several erosional calculations over the last 25 years, and I get numbers in that ballpark. For instance, I've done calculations for the Central Appalachians, got 6,000 meters of erosion. Namibia, Africa, 2,500. Southeast England, 1,600 meters. Northwest Colorado Plateau, 4,200 to 5,100 meters. And we're still working on a research project in central Montana, but it looks like it's going to be around 2,000 meters of erosion. And from the literature, you can get other estimates. Now, it's estimated that the whole Colorado Plateau, about 135,000 square miles, you've had an average of 2,500 to 5,000 meters of erosion on the whole Colorado Plateau. And by the way, there are at least 5 ways to estimate the amount of erosion in an area. And then in southern Arizona, more than 1,600 meters, 2,000 meters southern Rocky Mountain foothills, Canada, 6,000 meters Flinders Range, South Australia, 1,000, 3,000 meters southern Africa, 8,000 to 11,000 meters above the Vredefort impact structure of South Africa. Whoa, that's on the shield of South Africa. And 5,000 meters above the Sudbury impact, southern Ontario, which is in the southern Canadian shield, indicating that we've had a lot of sediments over these shield areas in the past, which I'll make a comment on later. So here's a diagram I use for the flood to kind of put this all in perspective. This comes from Taz Walker's biblical geological model, just based on the flood. Doesn't matter what the geological column says, even though we know where formations and fit into this in a lot of cases. Anyway, you can divide the flood up into two stages. A flooding stage where the water rises to a peak, and the retreating stage where it retreats off the continents when we're coming up out of the flood waters. But you can subdivide into phases. And the first phase is probably the most violent phase, where it rained 40 days and 40 nights, and the fountains of the great deep open and burst open, and the floodgates, the windows of heaven were open. And then based on those, it rained 40 days and 40 nights. So that's probably the most devastating, is the first 40 days. We call that phase 1. Phase 2 is where it was prevailing, with probably a gradual rise in the flood waters after a rapid rise in the first 40 days. And at the peak of the flood, at day 150, the ark grounds in the mountains of Ararat, and the fountains and windows were closed then at day 150. So that's probably the peak. Most Hebrew scholars that have studied it believe that the peak of the flood was day 150. So I've gone into a little bit. I think that's correct. And then the flood waters start retreating as the continents were coming up and the ocean basin sinking, called differential vertical tectonics. So after day 150, which we'll call stage 3, which I'm not sure what happened, phase 3, right there. I'm not sure what happened at the peak, but things reversed from sedimentation in the first 150 days to erosion of the top in the next 271 days. And during the retreating stage, when very few mountains and plateaus stuck up above the floodwaters, the currents would probably be 1,000 miles wide and 5 miles deep, moving across the earth and eroding huge chunks of strata and moving very fast in places. Then as more mountains and plateaus stick up, the water's forced to go around these objects. And that's this phase 5, what I call the channelized flow phase, where the water is more channelized, and it becomes more and more channelized until you end up just with the rivers after the flood, after day 371. So the retreating stage, when we had all that 1,900 meters of erosion, was in phases 4 and 5. of the flood, 1,900 meters eroded. So we have to place that back at day 150 to add to what was still there, and that'll tell us how much sediments were eroded for the first 150 days. Now, during sheet erosion deposition, which is phase 4, when you had to remember wide currents, moving at high speed sometimes across the earth, eroding the continents, you developed a number of features on the surface of the earth in the field of geomorphology that secular scientists have great difficulty explaining. And by the way, this is one whole talk, so I'm just going to mention these 5 features and make a point on planation surfaces in the continental margin. You can see the 5 there. Planation surfaces, numerous erosional remnants, long transported hard rocks. In my area, hard quartzite in the western Rocky Mountains was transported up to 800 miles to the east-northeast into central Saskatchewan, southwest Manitoba, and western North Dakota. And you formed coastal escarpments as the water was running off and the continental margin. So I have a few little slides. Here's kind of the big picture, wide currents moving across the earth. And here's a planation surface right here. This is a small one in the Bighorn Basin of northeast Wyoming. Here's the sedimentary rocks. You can see them tilted down. They used to probably a dome that went up like this. But whatever was there was sheared off flat, forming a planation surface. And there's about 15 feet of rounded rocks from the action of water on this. And it continues in the foreground here. You can see some of the rounded rocks. And it's been dissected after formation by probably very late flood, more channelized erosion and post-flood processes. But it used to be a lot more continuous in the northern and central Bighorn Basin, this planation surface, and it's really flat. And by the way, planation surfaces aren't forming today. So that's the key feature. And here's a larger planation surface in southeast Alberta, Canada, or southwest Saskatchewan, Canada. Right here. It's been dissected right in here by probably glacial runoff. I found big erratic boulders in this valley here. But anyway, you can see it's dead flat and has 75 feet of rounded rocks on the top of it. And yet it's a high plateau that's been eroded up to 2,500 feet all around it. And it's sticking way up in the air, 80 miles long and 20 miles wide, dissected in a few areas. And flat as a pancake, sloping down to the east, 75 feet of rounded quartzites from west the Continental Divide and the western Rocky Mountains. We know this because it has paleocurrent directional indicators in those rounded rocks. It indicate it came from the southwest, and the nearest source is central Idaho. Tremendous catastrophism, all this indicates. But anyway, I talk about these in other locations, but here's another diagram. You can see the scale, 400 kilometer scale, this big scale. Continent, the center, waters are running off, the continents are coming up, the ocean basin sinking and eroding flat surfaces from a more curved surface. And it's eroding it and depositing it on the sinking continental margin. As time goes on, you erode an escarpment, like a waterfall eroding along the edge right here. And the margin sediments thicken. And then when it's all over with, you have a planation surface called the African surface. The African surface covers about 60% of Africa, a planation surface. But it's been faulted and folded. So sometimes it's at different altitudes in Africa. 60% of Africa is a massive planation surface. And along the edge, we have the Great Escarpment. That escarpment's all around southern Africa, at least 3,000 kilometers long, all around it. And it's around a kilometer high, but off southeast Africa, it's 3 kilometers high, called the Drakensberg. And then then you have the coastal plain, then you have the thick continental margin sediments. This can all be shown as from flood runoff, especially during phase 4, when you had wide currents called sheet flow across eroding the continents, the planation surface, depositing off the continental margin, where the water velocity would slow down. When it slows down, and then it drops its load. So it's a nice picture, forming a unique profile called the continental shelf and slope. And here is a picture of the continental shelf off Los Angeles, California. And it's very flat. It deepens slowly, and about 130 meters deep on the average is where you meet what's called the continental slope. And it's a steep drop off. Now, that's a very unusual profile, by the way, because if it was slow processes, uniformitarianism over millions of years, you have sediments that are deposited in rivers, and then they get spread along the coast, and then they get sloughed down into the deep sea by landslides or going down through a submarine canyon. So you should have a gradual drop down to the deep sea, this dashed line right here. But you don't. You have a flat area or slowly dropping, sometimes over 100 miles. Some of these are maybe about 400 miles long, and then the drop off. That is like a delta all around the continents, everywhere, indicating sheet wide currents depositing way out and then a drop off. This is a very unusual profile that shows that powerful evidence of flood runoff. And Lester King, my favorite geomorphologist from the University of Natal in South Africa, in his last book, indicates how mysterious the continental margin is. And the reason why, briefly, the continental shelf is too wide. It goes way out there, and towards the outer edge, too deep to have been controlled by normal wind-generated waves of the ocean surface. It's just an unnatural profile. But the flood can explain it by rapid deposition as a delta all around the continents. So that was in phase 4. Phase 5 is another whole talk. I've developed all this stuff. In fact, you can get a free ebook on my website going through all this stuff, about 800 pages worth, all color pictures. It's from beginning to end. Anyway, mainly just on the retreating stage. Here it becomes more channelized, and it produces more different landforms than during the wide current phase or sheet flow phase. And I'm just going to mention those. This is all, well, the continents coming up out of the floodwaters were eroding 1,900 meters. You form valleys and canyons rapidly, like Grand Canyon. Water and wind gaps. Grand Canyon's a water gap, the longest water gap in North America, but not the deepest. Hell's Canyon between Idaho and Oregon is the deepest water gap at about 1,800 feet. Did I say that right? No, 8,000 feet. But the Snake River should have continued from southern Idaho into southeast Oregon, but instead goes north and cuts through the mountain ranges in a deep water gap 50 miles long. Pediments, which are planation surfaces at the foot of a mountain, indicating rapid flow down the valley, and submarine canyons. These can all be formed rapidly during flood runoff during the channelized erosion phase 5. And like I said, I have one whole hour of talk just on that. So, you eroded 1,900 meters. We still want to know how much sedimentary rock is left, because that tells us how much collected early in the flood to day 150. Well, how much during this part right in here to day 150? Well, we went into the literature. And there's problems with that sedimentary data because a lot of the estimates used, older estimates use poor data. And usually just some of the newer estimates are usually just only North America. And then some of the estimates include various proportions of the continental margin, which would be included in the oceans in this GlobeSed project. So we can't use that. And then how much Precambrian sedimentary rocks are included? They use variable amounts. Some use very little, some use a lot. So we get quite wide estimates of the average depth of sediment remaining on the continents. So guess what? We're doing our own estimates, and we're going to stick to North America, which we know best, and we're going state by state. We've done much of the Midwest, and I'm going to showcase this for Colorado. John Reed is doing the heavy lifting in this research project. And we've estimated the flood sediment volume and thickness left in Colorado after the erosion. And the way we do this, we have a whole step process. And you can apply this for any area or any state or portions of any country or a whole country, for instance. And I'm not going to go through this in detail, but usually you start with the geological maps and use well data. Put it in these big mapping softwares, Global Mapper and Surfer. I don't know anything about it. John Reed, like I said, doing the heavy lifting. And he create a three-dimensional basement surface. Basement being the depth below sea level of the igneous and metamorphic rocks of the upper crust. How deep are they? And then you take that difference from where the bottom is and to where the present topography is, and you get a thickness of and volume of sediment. And that I'm going to shortcut this, but this is for Colorado. And these are depths below sea level. This is only for depths below sea level. You can see that if you look at this, this map, and these are the contours, and the yellow areas are sedimentary basins. This gray area is where the upper crustal rocks, the igneous rocks, are above sea level. In fact, up high, these are the Colorado Rockies up to 14,000 feet. So there's no sediment there, except for we have some little parks in here, North Park, South Park. And here's a big volcanic area called the San Juan Volcanics, and we don't know if there's sedimentary rocks below it or not. I have pictures. I just need to run through that. But we didn't use this area or this volcanic area or this. And so we used all these areas. The white area has sedimentary rocks too, but the yellow areas are deep areas. So to get ground truth on this from the state geological surveys, we used well data. And there's quite a few wells in Colorado. In fact, some states were finding well over 1,000 wells that add a lot of information and data to this estimate. And you can see the green dots are wells that were added to showcase it. Now remember, these are elevations relative to sea level. Like this is a little uplift here that is covered by sedimentary rocks, but it rises 3,651 feet above sea level. So the numbers represent elevations of the Precambrian surface, that is the igneous rocks, relative to sea level. So those maps I showed you were relative to sea level. So we have to add all the sedimentary rocks above sea level in Colorado. And when we do that, we get these kind of figures right here. Depths down to the bottom. And we get an average of 1,931 meters for the whole area, including all this area averaged in for the whole state. So here's a dividing line. Now, if we only use the areas with sedimentary rocks, The average depth was 2,362 meters. And then because we have the Colorado Front Range and igneous rocks up high, if we wanted to average the whole state, we'd have to include those just part of the average, even though they have no sedimentary rocks, 0. So that's why we have 1,931 meters for the average for the whole state. And here's the average thicknesses for the various basins in Colorado. Denver Basin, about 2,898 meters deep of sedimentary rocks. You can see as you get west to these basins, they have deeper. The Piceance Basin is 4,294 meters. Average. These are averages. There's some places a fair amount deeper. And the San Wash Basin, that over 5,000 meters. Like I said, those are averages, but when you plot it up, you find areas that are deeper within those basins. And so here's a plot in feet. The Denver Basin, it's contoured every 2,500 feet. You can see the white areas that weren't included because they either had volcanic rocks down here or igneous rocks in here. And so this is the Piceance Basin, where there's an area over 20,000 feet deep, right in that red area there. And up in here in the San Wash Basin, it's over 20,000 feet. So we think that Colorado is probably close to the average, but we're getting numbers from of the sediments left, but we've only done the Midwest. When we do the Western United States, we're going to run into a huge amount of problems because of all the faulting and erosion and deep basins there too. So like the Belt Basin in western Montana is over 20 kilometers deep of sediments, and the bottom hasn't been found and the top's been eroded off. So huge holes and basins. Anyway, we calculated 1,900 meters approximately was eroded off, and about 2,000 meters are left. Now we're going to refine this later on and make it 3,500 to 4,000 meters total, but what is left is 1,500 meters to 2,000 meters. But right now we just about 2,000 meters. So that means the total sediment at the peak of the flood is about 4,000 meters, average over all the continents. What does that mean? It means that in 150 days, you had to erode all that sediment and deposit 4,000 meters approximately by day 150, of which the top 1,900 meters eroded off. So here's kind of a summary. This is why I call them incredible new flood developments. 4,000 meters need to be generated in 150 days. Whoa, that is a tall order for any flood model. And the deposits, not counting the runoff deposits now, were deposited only on the continents, but not in the present ocean basins. We do not have sedimentary rocks in the current ocean basins. What we do have are sediments that ran off after day 150, but sediments didn't deposit there in the first 150 days. And for North America, Cenozoic sediments probably didn't originate from the continent, may not have originated from the continent. Why? Because North America has been carpeted with a fairly thick layer of Paleozoic sediment over most of the area above the Precambrian sedimentary rocks that are in the basins on the continent. So this presents a conundrum for any flood model. Where did the sediments come from? They must have been generated by a powerful mechanism. Could catastrophic plate tectonics do it? They do have a model and it's reasonably good. I think it's got some glitches in it, and John Baumgartner and his students are working on it, but I still think it's might have a problem, but I need to analyze it more. Also, we need a powerful transport mechanism to deposit probably from off the continent, from the present ocean basins onto the continent. So what are we talking about? We're talking about radical new flood developments, and they'll be controversial. I'll be getting a lot of pushback on this, but we feel that the day 150 average sediments, about 4,000 meters, is a pretty hardcore data point, and that's what we have to account for. Here's a map of the Tapete sandstone, which is the bottom layer of the Cenozoic sediments, Cambrian, and this is where it's seen in the United States, and it goes up into Western Canada, up into Northeast Canada, and up in this area, the shield does not have any Tapete sandstone, but the next formations above that were deposited on the shield up in here. So you had deposition of not only Paleozoic, you had Mesozoic and Cenozoic on top of all these in a general order of this, all up in this area here, including this area. So that's where the sediments collected. But how could they be eroded from any of this area right in here? It's possible they might have come from the west coast somehow, or they could have come from off of the igneous and metamorphic rocks that are on the east coast, but that's a pretty small area. I'm thinking that we have to consider the ocean basins, that they came from the ocean basins, which suggests that possibly, and this is speculation, I admit, that the pre-flood oceans were on the present continents, and the pre-flood continents were where the present ocean basins were in general. And I call it the big switch. So if you have the continents down like this, collecting the sediments, pre-flood ocean up like that, eroding down like that, and then as the flood ran off, you'd have the continents rising, ocean basin sinking, and the water eroding 1,900 meters of those 4,000 meters, forming the continental shelf and slope. So I think the sediments possibly is from the present ocean basins. There are some paleocurrent directional indicators from the ocean onto the land in some areas. That's an area I need to research more. And it implies continental crust was once lower than the present ocean crust. And to drain the floodwaters, the continents rose with respect to the ocean basins. Psalm 104, 6 and 9 is applying to the mountains rising, the valleys sinking down to drain the floodwaters, but I believe it happened on the large scale, the continents and the ocean basins. So here's a little diagram of that. I call it the big switch. Remember, this is all speculation. Anyway, this is day 0 of the flood. Here's your present ocean basins, which were the land, and your present continents, which were below the pre-flood ocean. And by the way, on the present continents, you have a surface called the Great Unconformity that is an erosion surface where it's been plain, generally flat with some erosional remnants over much. We see it in the western United States, either in the bottom of Grand Canyon or the top of the mountains in Montana and Wyoming. And you see the same thing on other continents, a great unconformity on top of the upper crustal rocks, the igneous rocks of the upper crust. And so the first thing I think formed in this was the great unconformity. And I think that impacts had to be part of the flood. There are some flood geologists that have essentially rejected impacts, but I'm going to make a case that they need to be considered. And it's these impacts hitting that I believe cause huge currents, like this one hitting the ocean, going that way, and that eroded the sediments and caused the flat great unconformity on the present continents. And this got torn up so bad that it ended up being material eroded into the on top of the continents. So about day 80, the present ocean basins are coming up because they're losing sediments, and the present continents are gaining it. So they're kind of sinking isostatically as the water comes off. So by day 150, the whole Earth is flooded, and you have about 3,500 to 4,000 meters of sediment at day 150. And then things are going to reverse like this. The present continents are going to come up. And by this is trying to represent the deep troughs along the continental margin. And these are the coastal mountains. And the sediments are raw, forming the continental shelf and slope sediments. This day 250. And by the end, the present continents are risen up with only 1,500 to 2,000 meters left, 1,900 meters eroded, forming the continental margin sediments right in here, and so a little bit of ocean bottom sediments. So I think that's a possibility from what we see based on where the sediments lie right now. So this is rather radical. And not only that, it has something to say about the Cenozoic of the geological column, in that most of the continental sediments, remember, you eroded 1,900 meters off during the retreating stage after day 150. So what's left, whether it's Cenozoic, Mesozoic, Paleozoic, Precambrian, that has to be from the flood. And some of that in the Rocky Mountain valleys and the high plains of North America are labeled Cenozoic with mammoth fossils. So they'd have to be early flood in this scenario. And then the sediments laid on the continental margin, a lot of those are Cenozoic, and they would be from flood runoff. And some of the deep ocean sediments of the Cenozoic could be post-flood, mainly because they claim there's ice-rafted debris in some of the Cenozoic sediments. And ice rafting didn't start until probably well into the ice age after the flood, which should indicate that those Cenozoic sediments, where you find these ice rafted debris, as they call it, if it's truly ice rafted, now that could be questionable. But regardless, some of it's in Cenozoic. So that would mean that some of the sediments on the deep ocean, the Cenozoic sediments, could be post-flood. Here's a kind of a schematic of this. I should have put the coastal mountains right there to kind of blend in from those previous schematics. Oh, and by the way, these diagrams and much of my artwork is done by Melanie Richard from Billings, Montana, who also does the murals and the dinosaurs in the Glendive Dinosaur and Fossil Creation Museum in Glendive, Montana. Fantastic museum. If you've never been there and you're passing through, I think it's I-84, Interstate 84. It's right off the freeway, and you can go in there and tour the museum. It is a high-class museum, by the way. It would surprise many of you. And Melanie has done practically all the artwork and the sculpting of dinosaurs and painting them. But anyway, she's my artist. And so anyway, here's the early flood sediments right in here in the Rocky Mountains. This is the high plains. And people think that the Cenozoic is either post-flood or late flood. Well, that can't be on the Rocky Mountains. And and there's several other features of this, is that you find mammal fossils not only in here, but you find mammal tracks. Tracks are from a live animal, like dinosaur tracks. And these have to happen in these sediments early in the flood, before the mammals were all dead. So it all makes sense. It's a nice picture of flood runoff. But these sediments were formed late in the flood, during flood runoff. So those Cenozoic are late flood. And in the bottom of the ocean sediments, some of those could be post-flood. But no one really knows exactly, because like I said, you have a massive amount of data on the ocean bottom sediments and even into the igneous rocks that no thousands of drill cores, and no creation scientist has done much into that. I have dabbled a little bit in it, but it's a massive amount of data that may tell us something. So I lean that meteorite impacts or comet impacts can explain the flood features. First of all, an impact, it hit either sediments or igneous rocks or in the ocean, and it would blast up a huge amount of sediment up into the atmosphere and even beyond that gets sucked down by gravity. And so you can generate the sediment by just blowing off portions of the upper crust. So that's how you can get the sediments to start with. You got to generate those sediments by some powerful catastrophic mechanism. Impacts will do the job. I'm not sure the other flood models like Walter Brown's hydroplate model or the catastrophic plate tectonic model can do it, but I think they're working on it. Maybe they'll have a good theory out soon. Also, impacts hitting the pre-flood ocean would blast all this water up. They would get caught in the upper winds and be spread all over the earth and would come down as 40 days and 40 nights of global heavy rain. Impacts can explain that really well. Also, an impact hitting the ocean would cause huge currents, maybe currents going 200 miles an hour with huge turbulence. These would erode the great unconformity and also transport those sediments for a long distance. So I think you can explain the great unconformity that way, and other unconformities, especially angular unconformities where we have sedimentary rocks tilted, say, vertical, like in Scotland, with flat sedimentary rocks on top of it. This was Hutton's key type area for rejecting the flood. Said the flood couldn't do that. Well, with impacts, floods can cause vertical strata that can be planed off flat. Then you put flat sediment on top of it. So impacts can cause these unconformities. Also, a strange feature of the sediments. Unlike sediments today along rivers, which are mostly conglomerate, you find hardly any conglomerate in the sedimentary rocks. It's overwhelmingly 99 point some odd percent fine-grained sediments, silt particles, quartz arenite. Those are some unique. Quartz aranite's a sandstone that is with rounded quartz grains, practically all quartz, a very unique sandstone, which I think can be formed with this model. And then the resulting sediments are fine-grained. They've been ground up, turbulence, fast currents, down to fine particles. And they even speculate, this is more speculative. I think those first five there are, I think they're pretty reasonable. But that sixth one is speculative. I got to think about that, because if you know anything about the geological column, there's a certain order. And I'm just going to talk about the broad scale order, in that the Paleozoic is mostly marine creatures, and they would be accounted for with sediment carpeting the continents early in the flood. Then above that, you have the Mesozoic with dinosaurs, and then above that, the mammals. And not only that, the upper Mesozoic, you start getting diatoms, which is a marine plankton. Down below the upper Mesozoic, you don't have any diatoms. Why? Also, you get flowering plants in the upper Mesozoic and the Cretaceous. Why? And none below. Well, I think it's because of the environments. The environments were being eroded, mainly probably based on elevation. And so the first carpeted North America, I'll just use North America, you can apply to other continents, with Paleozoic marine sediments. Then currents came, say, from the west, which I think is the dominant current direction in Mesozoic sediment. We're bringing organisms from different environments, and it spread dinosaurs from an environment, maybe a low altitude environment out there in the Pacific Ocean, and deposited on the marine sediments And then finally, you get diatoms from a totally different environment and flowering plants deposited on all that. So you might be able to account for certain broad, large-scale fossil order in the geological column by this model. And we're just beginning to, because it has a lot to say about the flood. So we're continuing to do research. This is going to result in multiple papers. We have sent 2 into the Creation Research Society Quarterly. But to defend flood impacts, there's been about 200 confirmed impacts. The secular scientists, but there's reasons for a lot more. Nothing like what I estimated earlier from using the moon as an analog. So I think the total, I'm getting at, including the ocean basin impacts, something around, and the possible impacts, there's 200 confirmed. There's at least double that are possible impact features. And there's impacts on the ocean. So I get about 1,800 meters as a maximum. But regardless, I don't have to use that at all. Let's just talk about what the secular scientists have confirmed as impacts. And I'm just going to talk about the 2 largest impacts. The Vredefort impact crater, 250 kilometer diameter, is a conservative estimate. The impactor would be 28 kilometers in diameter, and it would destroy 9.5 times 10 to the 7th square kilometers of the surface. And by that, destroy, I went to a program that tells you what impacts do, how big the fireball is, the wind gusts especially, and they go way out. And I used the wind gust of over 50 miles an hour as a threshold, 50 meters per second, I mean, which is about 113 miles an hour as the threshold of destruction. And the program says that practically all houses would be flattened, and 30% of the trees would be flattened with a wind gust of 50 meters a second. And so that's why the damage area was in this area right here. The Sudbury impact is a conservative estimate, is 200 kilometer diameter impact. They've been eroded. The impactor is 20 kilometers in diameter, and it would destroy 5 times 10 to the 7th square kilometers of the surface. When you add them both up, which you can do because they're practically on different sides of the globe, they both would destroy 14.5 times 10 to the 7th square kilometers of the pre-flood surface. The area of the present continents is 14.8 times 10 to the 7th square kilometers. So those 2 impacts alone, if the continental area was the same before the flood as after the flood, would destroy practically all the surface of the pre-flood continents. And these were continental impacts, by the way. Those 2 alone would destroy the surface of the earth. So impacts need to be included in any flood model. And when you add impacts, you add a lot of energy. It's possible, I think, that flood impacts could have started the flood. Or if you want, flood impacts could be part of the catastrophic plate tectonics model, which I accept 20%. I think 20% chance of being right. But I find a lot of glitches in it when I read those earth science journals. They seem to find me. I don't really focus in on this much, and I don't spend a lot of time on it. But there's enough glitches in that model, and especially plate tectonics. Catastrophic plate tectonics, I think, can explain some of the problems for plate tectonics. But there's still enough glitches that it needs to be explained. Anyway, one of these days I might accept it. I'm open. Anyway, impacts have to be included in any flood model, just based on these 2. And another interesting conclusion in all this is that those 2 impacts that I showed you, they occurred about 2 billion years ago, they claim. well down in the Proterozoic, right down in here. And they find impact spherules in Archean sediments up to, I think, 3.5 billion years old, according to the secular time scale, which I'm using just as a relative time scale, by the way. So, and those impacts would be huge. So if you had huge impacts down in there in the Precambrian, well down the Precambrian, where does that say the Precambrian fits into a flood model? Now, some people think the Precambrian is a record of creation week, and some people think it's a record of the pre-flood time, and that the flood started at the Precambrian-Cambrian boundary approximately. So all the Phanerozoic sediments above the Paleozoic, the Mesozoic, Cenozoic is all from the flood, but that below is considered either pre-flood or creation week rocks. But that can't be. If you have these huge impacts way down in the Archean and Proterozoic, and that would imply that the Precambrian sedimentary rocks are practically all from the flood. And I believe from the early flood, trapped in deep basins created early in the flood, rifts, impact craters, and they filled with these Precambrian sediments rapidly. So this is implying that the pre-flood flood boundary, assuming the geological column, for sake of discussion, is way down in the Precambrian. Now, this is mind-blowing for a lot of people, but to me, it appears reasonable and straightforward, and I don't think that is very speculative, not like the big switch. This results in numerous research questions, and I'm going to get pushback. For instance, the isostatic effects. The continental crust is light, and the ocean crust is heavier, basalt, and they kind of float on the cenosphere in the mantle. And the question is, how can the continental crust be below the ocean crust before the flood? Well, the thing is, with isostatic effects, you got to include all the mantle too. Just can't include the crust. But I need to go into it, and I'm going to get some probably heavy pushback on this. And how does it affect the geological column? I showed how it affects the Cenozoic. The Cenozoic could be early flood, late flood, or post-flood, depending on where you find the sediments. So what about the Mesozoic and Paleozoic? Well, I kind of generally think that they can be generally correlated, but there might be some glitches in that too. How does this result affect Tim Clary's megasequences? I'm not sure yet, but it's a research question for the future. And then we have the issue of, for the ocean crust is basalt. How does this figure into all this? I don't know yet. I'll look into it. And you have these mid-ocean ridges and fracture zones. Even though the catastrophic plate tectonic model think they can explain those, I think they have problems in that model. Namely, they're so sharp looking, and the fracture zones are perpendicular. The sequence has the geomorphology of extension. I want to pull it apart and quickly, where the mid-ocean area rose and the abyssal plain sank. So you'd have fracturing of the mid-ocean ridges by the mechanism, I believe, differential vertical tectonics later in the flood. I think that, but I still have to explain all that. So these are research questions. And if you want to know more about certain features of all this, I have a whole book on the flood runoff. And what was left is just amazingly beautiful mountains where I live, 5,000 feet in the northern Rocky Mountains of North America. And anyway, the flood by design, receding water shapes the Earth's surface. And I've written 5 children's books, of which 2 are on one's on geology. I mean, I'm telling you about these so that if you want to go into it in more depth, this is mainly for young people and adults. I also have one on dinosaurs, and here's my latest book for those people that just new to this area, want to know how all this stuff fits in, and to look around as they drive around, see where things fit. With Robert Carter and we wrote Biblical Geology 101. A great book, color pictures, well done by CMI. I'm really pleased with this book. And now you probably have a lot of questions, and hopefully I might have some answers. So I go back to you, Donnie and George.
Mike, thank you so much. And you're right, we have a ton of questions here, brother. So hopefully you're okay to be here to probably same time tomorrow. Just kidding, of course. I want to say, Mike, as always, extremely informative. And the title is perfect. I've been excited for this, and incredible new flood developments. That's absolutely right. Mike, I appreciate all your hard work and diligence. And I got to say, I will definitely be adding your new Biblical Geology 101 to my library. So
Okay,
that
good.
looks fantastic. George, we have a ton of questions, but I know you had a couple things you wanted to add first, and then we'll get right into these because we have a lot of interesting questions as well, very on topic. So, George.
Okay.
Yeah, Mike, I forget the person who asked the question about the calculation of the volumes. I mean, I was involved as a junior engineer in determining the volume that was going to a landfill. We call them tips, on an annual basis. So what we did was, before we even started dumping material in that tip, we got a basement layer. So we used the theodolite, got all the levels of the basement. Then each year we did a resurvey of the new fill that went on top, and we did a finite element analysis by creating triangles on that surface to determine the difference in level from the base layer to the new layer. And we were able to calculate the volume, and we did that on an annual basis. And we could then find out how long, what kind of life was left in the tip, how much material was being dumped, how much money we were generating out of it, etc., etc. But one of the other things that I want to add to your presentation, Mike, is the incredible amount of work that creation research, that's John Mackay, has done on layering, and he's done heaps of flume experiments. And Donnie, I'd just like to share my screen so I can show Mike, because I'm not sure whether he's aware of the type of geological features we can actually create in a flume experiment. Most of us are aware of flume experiments where we create horizontal layers in a sideways pattern from, say, upstream to downstream. But this is going to blow your mind, Mike, if you haven't seen it already. So, Donnie, please share my screen.
Sure.
And I haven't. I'm not aware of this.
Oh, well, get ready. Can you see that, Donnie?
Yes.
Okay. So you can see there, Mike, not only did we create layers, but we also created these anticlines and synclines.
Mm-hmm.
And this was done by varying certain parameters like velocity of the water and the direction of the water. In this particular case, we simulated water coming from the Great Deep. So you can see that geological feature there. That's a flume cross section. You could pretty much match that with any geologic book where they've got similar type cross sections of actual geological layers. And of course, this is further. You can see there's a fault being introduced. That's not due to uplift or anything. It was due to the introduction of water from below. There you go. Yes, the fractured straight line was caused by water, not by earth cracking. And there's the flume. So if you don't believe me, that's the flume there. You can see the various layers that were formed. So the layers were coming from the right to the left, but the layers were forming in reverse in the middle. And you can see some of these fantastic geological features that you'd never believe these were formed in a flume, but they were. Okay, so here's a good comparison. The bottom picture we all seen in geology books, and the top picture is an actual flume experiment that John Mackay had performed to show how similar they look and why you don't need millions of years. In actual fact, that top picture there, Mike, was created in 20 minutes. In 20 minutes.
Yeah.
And not only that, but using rotary flumes, you can see they created both the layers and the landscapes. So we can answer a lot of these questions that are put forward to us by these skeptics out there. The other point I wanted to make before we go to the questions was I think there's a skeptic in the chat. I'm not sure if he's still here, but his name's Mark Siegel. He claims to have studied geology. Well, a lot of us have studied geology, but, you know, having qualifications and practicing in geology is a different thing. But one of the things I wanted to point to him is the Tapeats sandstone. I believe you touched on it.
Yes.
And you're probably aware of the actual testing that Andrew Snelling, Dr. Andrew Snelling, has done on those 90-degree bends. Now, the secular explanation for those bends is they occurred due to lateral compression deep down in the crust at about 4 kilometers, you'd need the amount of heat to bend those layers without cracking. But here's the point, Mike. Under that kind of heat and pressure, you'd expect to see crystallization in those 90-degree bends. Well, I think Andrew Snelling is about to write the paper. He's dotting his I's, crossing his teeth, but there was no evidence of crystallization in those bends. Hence, there was no heat involved. There was no metamorphosis in that process, which debunks the secular explanation that those 90-degree bends occurred 4 kilometers deep under the crust and then were later uplifted. So that's what I wanted to add to that. But Donnie, I know looking at the private chat, there's like 100,000 questions. So I think we're going to have to be selective about which ones we choose.
I want to make one comment.
Go ahead.
McKay and any colleagues should publish this, because if you don't publish it, it doesn't really help us learn more and bless everybody else to build the flood model and answer a lot of challenges that we have. So encourage them, if you talk to them, publish. I want to see
he does intend to do that. I think he's hasn't finished all the flume experiments yet. I think it's up to version 12 or something, but he's going to definitely release a book on it showing all those illustrations.
Oh, okay. Well, you don't have to totally finish. If you find some good results, get it out.
Yeah, exactly.
So
all right,
that's
Donnie,
why
maybe. Yeah.
Very good,
Donnie,
gentlemen.
you want to fire away at the first question?
Sure. Yes. I appreciate it, gentlemen. You guys make a good team. So an encyclopedia worth of information here between Mike and George. So I'm going to start with some of the questions that came in even before we went live. So, we set the event, and Mike, you're a fan favorite. You're a blessing. So we had some questions come in even before the show. So here's one of them. And this question is, I've got it up on screen. If the flood boundary is lower than the Cambrian, then do you still think the Great Unconformity marks the beginning of the flood?
I do not. I think it was towards the beginning, because the reason I don't is because the early part of the flood, you caused a lot of rifting and impact craters on the continents. And the Great Unconformity, I believe, is formed by very fast currents and turbulence. And that's going to take some time to do that. So it might take 20 days to form the Great Unconformity, for instance. and then you get the Cambrian sediments deposited on there. But the currents have to slow down some, or you're not going to deposit sediments. That's the key. I think for the Precambrian, they're mostly in basins and rifts, and those are kind of sheltered areas when there's a lot of turbulence and fast currents forming the great unconformity. The sediments are deposited in these basins, and that's where the Precambrian rocks are practically all located. Those basins have since deformed, a lot of them. So I'd say the great unconformity maybe took 20 or 30 days at the very beginning, and then the current settled and slowed as the mechanism of the flood waned. And with that slowing, you had what I call the Great Deposition. That's where you find the Phanerozoic sediments from the Cambrian all the way up, like in the Colorado Plateau, which probably has somewhere around 15 kilometers of sediments in many areas, or 10, let's say 10 kilometers, that you can determine, and where you can see it, like from the Grand Canyon, the Grand Staircase, and other places. They're a little deformed. You don't see big faults in them. It's as if they are all deposited, at least on Western North America. It's the same up in my area of Montana and Wyoming. They seem like they were deposited quickly with little deformation in them, which would be, I would say, well after the very beginning, I'd say after day 40. I think the vast majority of the Phanerozoic sediments were between day 40 and 150, plus 1,900 meters more on top. So now I think the great unconformity in the Tepete sandstone was maybe about day 30, day 40 in the flood. It's not can't be very beginning, because it takes time to form the great unconformity.
Yeah, Mike, if we did get 1,900 meters of erosion, I mean, that can explain why we don't find some of the fossils that the skeptics say, yeah, but why don't we find human fossils? Because there was obviously a lot of erosion. And the other thing is the great unconformity does show tilting, but when you look at the Tepete sandstone, which sits directly above it, and that has 90-degree bends, if the 90-degree bends, as secular science claims, was due to lateral compression and uplift, why weren't there any bends in the great unconformity layers? They're only tilted, they're not bent.
The great unconformity is an erosion surface.
Yeah.
You're talking about the sediments above it.
Yeah, that's what I'm saying. If obviously in the secular explanation I'm talking about, if they were deep down and there was lateral compression of the Tepete sandstone, then why don't we see compression events in the great unconformity? Anyway, maybe it's a bit of a digress there, but
no, the sediments above it, you don't. In North America, they find a lot of faulting. You don't see within the sediments themselves much deformation or faulting within them when they're deposited. It's always after they're deposited, which would occur after day 140 as the mountains are coming up, the valley sinking down, a lot of vertical tectonics.
Yeah, correct. In our model, it makes sense.
Very good. Very good. Okay, so here's the next question that comes in. Let me see here. This one comes in from Cool Jesus. Thank you so much for your question. And he asks a specific question for Mike. How does Michael explain unique flood era deposits, specifically gray fossil site, sinkhole, and the volcanic ash deposit in Ashfall Parks?
Okay. The gray fossil site, I'm not familiar with that, but I'm familiar with that ashfall. If it's the one in northeast Nebraska, I did a research project there, and it's a difficult area to know whether it came after the flood or before the flood. So I added it all up. A lot of the fossils were not Ice Age beasties. They were strange things you'd expect in the flood. Also, you had a lot of the gravel from Rocky Mountains that spread over that area during flood runoff, called the Ogallala Formation. Based on that, and the scale of this is a huge amount, I leaned that it was from the flood. Now, Carl Frody and Jerry Ackridge disagreed with me and thought it was post-flood, so we had a debate in the pages of the Creation Research Society Quarterly, but I would lean it's from the flood. Now, I would say 95% of the areas from the 33 criterion I've developed, I can tell where the flood post-flood boundary is. And there's 5% that are difficult. And these criterion I have multiple criterion because no one criterion is absolute. So you need multiple criterion. And some places are difficult, and the asphalt site is one. As far as that sinkhole, I believe sinkholes and caves, the openings occurred when the limestone solidified early in the flood and came up. As it comes up, it's expanding, and so it's cracking. And so a lot of water carrying acids, sulfuric acid mainly, they're finding out. I have a whole talk on this, by the way. It eats out the cave opening quickly. So cave openings, I believe I can show occurred during flood runoff when the continents were coming up and the waters were moving through those sediments and going through the cracks, widening them by acidic sulfuric acid reactions. So after the flood, you're left with all these openings. And only during the Ice Age, with heavy precipitation, different environment, thicker soil, more carbon dioxide in that soil, you form the features. You deposit the calcium carbonate instead of eating it out. You deposit the nice stalagmites, stalactites during the Ice Age mostly. So I have a whole talk on that. You might want me to talk on down the road, but that's one of many talks. But anyway, that's how I would explain a sinkhole. I don't think too many sinkholes formed after the flood.
Very good, Mike. As always, very informative. I appreciate the answer. The next question comes in from Mark Siegel, George, your best friend here. And he asks, oxygen isotopes in ocean sediment prove the Earth experiences a glacial period every 100,000 years. How do you explain this from a global flood and young Earth creation perspective?
Well, I've worked on that, and I'm going to have a new book out in about a year or two on the Ice Age with more detail and summarizing some of my past research. But I'll be talking a little more about this. And in the book I did on ice cores, I get into this more. Yeah, when you look at the ocean sediments in the cores, they have wiggles of variables, wiggle back and forth, and they run an average through it. And when it wiggles this way, it's a glacial. When it wiggles this way, it's a interglacial, so forth. And there's a lot of those wiggles. But I don't think those wiggles are due to glacials or interglacials. And by the way, it's only the last million years that they're 100,000 year sequence. But before that, they're every 40,000 years, clear down to 2.6 million years of the Pliocene-Pleistocene boundary. So there's about 50 of these wiggles. Therefore, they say there's 50 ice ages in regular succession. You might ask, why exactly 100,000 years or 40,000 years? This just happens to match two of the three cycles in the astronomical theory of the Ice Age, or the Milankovitch mechanism. So I've done a lot of research in this area, and what I'm finding is that they've assumed the astronomical theory. And so they've tuned deep sea core sediments and ice cores to the Milankovitch mechanism and dated by that. And so that's how they fit it into their paradigm. But in the post-flood rapid ice age, where you started with warm ocean water, and it cooled from the top down. Cooler water being denser, it sinks. It'd have to be replaced by warmer air. You have great overturning of the ocean. And so they can cause these cycles quickly. And so I believe that they're decadal cycles during the Ice Age that oscillated every decade or so. That's what I believe they are, and have worked on, and I think there's going to be more published on that. But that's how I would explain those cycles. Otherwise, they have 50 ice ages in regular succession. But the thing is, on land, you only see evidence in most areas of only one ice age. In the Greenland ice core, you see evidence of only one ice age. It's only along the edges of the ice sheets where you find oscillations, where you see complications, where you find glacial till, maybe sand above that, and then another glacial till, and maybe more things, even maybe a dead mammoth in there. But all that can happen at the boundary of an oscillating boundary of an ice sheet, which would, in the model I developed, where the winters are mild compared to today, and the summer's cooler, with little seasonal contrast, you'd have a lot of oscillations, and the ice would be what's called warm. And therefore, it can form a lot faster when it's warm, especially with particles and volcanic ash in it, than you can today, or during their ice ages where it's bitterly cold in their ice ages. Besides, the Milankovitch mechanism is very weak. The 100,000 year cycle doesn't even show up in the idea that it's based on the Earth's eccentricity. It varies slightly. The radiation effects are almost zilch, and yet they're stuck with that. The 40,000 year and the 23,000 year cycles are more significant, but they're small also. And meteorologists have been pointing out for 150 years how weak the idea is, but the secular scientists love it because it's the only thing they got. They got 60 theories, and that's about the only rational thing they have, because it can point to the changes in the Earth's orbital geometry. But that, as meteorologists have been saying for 150 years, they're very slight changes, and ice ages are dramatic. You have to get 50 degrees Fahrenheit cooling along the northern United States for the ice to develop there. So huge cooling in the ice age. So I think this is all a house of cards developed based on their assumptions and a lot of circular reasoning.
Yeah, I was just going to add, Mike, I was listening to a scientist from ICR the other day talking about this specific subject, and he mentioned the ice core data that they initially used to prove the Milankovitch theory, and actually contradicted it. And they went back and literally falsified the Milankovitch theory, but they didn't like that, so they went back and redid the ice cores, and they tried to find the data to fit the theory. I mean, that is ridiculous, isn't it? That's what we always say, that they try and fit data with theories rather than let the theory predict what the data should show.
Yeah, that's Jake Hebert that's done that research, but I've done some research on that, and this is a lot of the things I've said. And for our critics, our critic friends, in the 1997 Journal of Geophysical Research, Atmospheres, they had one whole issue on ice cores, and they went through the dating. They didn't go into the details, but anyway, I can't name the lead author at this point. It's a lady from Denmark, but anyway, they drilled down from the top of the Greenland ice core, the grip core, and when they got near the bottom, they counted annual layers. That's supposed to be very scientific, but there's a lot of glitches in that, I found. I have an ice core book on that. They only got down, when they got near the bottom, it was 80,000 layers, they claimed. But the paleoclimatologist said, that's not right. According to the Milankovitch theory, it has to be a lot older than that, 115,000 years. So guess what? They did a laser beam to get annual layers of dust oscillations. And of course, they used a finer laser beam. It went from resolutions of 8 millimeters down to 1 millimeter. And guess what? They found more wiggles. And they added 25,000 more years in the bottom 500 meters by doing that to come out to exactly what they expected. And that's plain as day in this article by Meese, Deborah Meese et al., 1997 Journal of Geophysical Research Atmospheres. So it's there sitting as plain as day what goes on. I think that's the tip of the iceberg. So, yeah.
Yeah, there's so much we can add to that, but I know Donnie's got other questions, so we'll just continue on.
Okay.
Donnie, are you there?
Yeah, I thought you were going to pick the next question. So I've got one here, Mike, for you. And this is a longer one, so I'll read it out. And the question is, since the KT boundary model, and I've read several articles from you on this specific topic, since the KT boundary model would have Cenozoic mammal fossils being the result of migration after the flood, would this not suggest gigantic post-flood catastrophes? And it's kind of a two-part.
Right.
Yeah.
Yeah.
And
I mean, yes, if that's true.
And so I guess the second part to it would be, would these moderate to high post-flood catastrophes make it difficult for mankind and animals to spread out over the earth?
Like I was said in that 33 evidence is that it's the boundary is very late, which would eliminate post-flood catastrophes. Mainly the Cenozoic has that period alone, compared to the Cretaceous, Jurassic, Triassic, etc., has more sediments in it than any other period in the geological column. So you had a huge amount of sedimentation. You had huge tectonics, 40,000 feet in the Rockies, for instance. That's all mid to late Cenozoic. But so I don't believe that the boundary can be down there. There's just too much Cenozoic history, even using the secular history, that says that too much happened. And for the mammals, yeah, they have to spread for the mountains of Ararat, increase by the millions, come around the Bering Land Bridge, and there's a lot of them in North America in the Cenozoic sediments, probably in the millions. And so they got to multiply, die, and then the top thousands of feet of those areas of that sediment got eroded off. Just the erosion, 1,900 meters, as I found out. After all that, then the mammals are below that. It's obvious to me that they're from the flood. And the whole idea that they round the land bridge, got into the millions, died, and died in a certain order is incredible. And not only that, you don't find too many mammals in the Mesozoic. So those people who believe that the Cenozoic is post-flood have to believe that hardly any mammals showed up as fossils in the flood, and a vast amount of them, millions and millions of them, ended up after the flood fossilized by some post-flood catastrophe that is very non-specific. They're very non-specific as exactly what these are. There's some hints, big landslides, but yeah. So, and the second part of the problem of what that is spreading from the mountains of Ararat all around the earth. Well, actually, if you include log mats in all this, after the flood, a lot of the floating vegetation, the logs wouldn't have sunk right away. They might still be in existence up to 200 years afterwards. And so they'll be moving around by the currents. And so animals that increase can move out onto these that are beached, and it unbeaches maybe because the tide rose, and they can spread long distances. In fact, that's how I believe the Australian marsupials and snakes and frogs and a lot of insect, a lot of other types of non-marsupial animals got to Australia. They couldn't have got there by a land bridge, and there's problems with deep channels, deep wide channels in Indonesia. So I think log mats and the secular scientists have realized that plate tectonics doesn't solve any of these issues of, like, say, for instance, how the New World monkeys in South America came from Africa, and also the what's called caviomorph rodents came from Africa. Well, I believe they came from the mountains of Ararat, but the only way I think they got there, I think they did raft, but the secular scientists rely on these small vegetation rafts torn up by a storm floating down a river or something. But the thing is that when they hit the ocean, they just get torn up. So that's not very good model, but we have thick log mat models, maybe 100 feet thick, large. They can be stable. They can transport across. Then you had a whole cadre of mammals that rounded the Bering Land Bridge. And early in the Ice Age, that land bridge was not bitterly cold in the winter. In the early Ice Age, winters were mild and summers cool. So a lot of mammals can easily have rounded the Bering Land Bridge and not be frozen to death. And so we could have got a lot of the North American mammals, Central American and South American, across the Bering Land Bridge. And you had a land bridge from Europe into England across what's now the Dover Strait. We know there was a land bridge there because there was a lake during the Ice Age trapped in the southern North Sea that broke through, and you see channeled scabland features on the bottom of the Dover Channel, indicating that a lake broke through and destroyed that land bridge. And that's why we have over 100 hippo fossils in England with woolly mammoths, reindeer, and musk ox in Ice Age sediments. The hippos got there when it was warm and wet because of warm onshore flow of the warm water and the warm air with a lot more precipitation. So the hippos lived there, but they got cut off by the land bridge breaking, and Ice Age animals moved in and they died together. So we have answers to a lot of these questions.
Yeah, Mike, on the log mats, I remember listening to John Mackay about the coal formation, and he mentioned I forget the location, but he mentioned a coal deposit in Australia, and the secular explanation to that is, these trees grew in swampy land and they fell over millions of years, were compressed, etc., etc. But he mentioned a specific example where they found a pine tree in polystrate fashion.
Mm-hmm.
And he said, looking at that species of pine tree, he goes, they don't grow in swamps.
Yeah,
so
that's the issue. And once in a while you find an upside down tree, by the way, in those polystrate. So
well, at Nova Scotia, you find reeds in the upside down position.
That's one place.
Yeah.
It's also, there's a spot in southeast Australia, that big thick Cenozoic coal seam that they mine there.
Latrobe Valley. The Latrobe Valley.
Yeah, Latrobe. Yeah, that's it. And that's dated, I think, middle Cenozoic, I think. But anyway, the swamp theory, that's a very poor theory, mainly because you have such pure coal seams in southeast Montana and northeast Wyoming. You have the Powder River Basin that has coal it has enough energy in that coal to supply our needs for 100 years. And some of those seams are up to 200 feet thick of almost pure coal. And if that was in some swamp and you have to compress it 10 to 1, you had to have 2,000 feet of swamp deposits. And the ground has to sink to collect all that stuff without flooding and all that. I mean, it's just mind-boggling. The pea swamp theory really doesn't work if you go into it in depth.
Well, if I could jump in great responses, Mike, to branch off from your previous answer, which was fantastic as well, my thinking is, and it has to do with the next question that comes in that has to do with mammal fossils, is
Right.
as you're pointing out, if most or even all, I guess, as the KT
Practically all.
So they would say the Cenozoic strata would be post-flood for the most part. So therefore, all the mammals have to be post-flood. But as you're pointing out, we have millions of mammals who would have had to adapt from archetypes, mammals that were on the ark.
Yeah. Mm-hmm.
Therefore, where are all the mammals from the pre-flood world in flood deposits? Because they would have had to been buried in order to have millions of mammal species come from mammals on the ark, correct?
Well, yeah, you have to have a spread. We'll focus on North America, which I know best. There's millions of mammals in the Cenozoic strata, and they'd have to spread from the ark, round the Bering Land Bridge, multiply. Did some huge catastrophe bury them, and then the top 1,000, 2,000 meters be taken off and taken clear off the continent. That to me is a flood signature. And also, if you believe all those Cenozoic mammals are post-flood, where are the mammals that died in the flood? There's hardly any mammals in the Mesozoic. And then you have to say that you had a huge amount that died after the flood and were fossilized. Well, hardly any during the flood. I mean, the whole thing is backwards, and it doesn't make sense to me.
Well, exactly. And like you pointed out, where are all the pre-flood mammal fossils then?
Yes.
And so my question, this is my own personal question that just came to mind based on what we're talking about here. Whales being mammals, if you hold to a KT flood boundary, and therefore all for the most part of the mammals are post-flood, would you have to say that whales are post-flood too? That are buried?
Sure. And, there are some ideas out there that the ancestor of the whales was some kind of mammal that left the ark and adapted to the water. This is kind of what the secular scientists have said.
Right.
But that doesn't seem to make much sense to me. That's about all I can say about it.
Well, that would be a lot of evolution in a really short amount of time then, if you had a walking whale on the ark that had to evolve into, as you pointed out,
yes,
ocean whales. So yeah, that's a very interesting point. Okay. Let me get to the next question here then, since we kind of answered this one that's on screen. Do most mammal fossils fit within the post-flood or pre-flood sediments? The next question here that would be most on topic. Let me get it up on screen. And okay. So question is, a late Cenozoic flood boundary means that what young Earth creationists traditionally think is the created kind is more close to a species or genus than at the family level. Do you have any thoughts on that, Mike?
Well, I think it probably would average at the family level. I don't see how that would follow. Sorry about that, cool Jesus. Well, even if they die in the flood, you find a lot of variety within these. I mean, you find, say, a lot of rhinos, a lot of horses, great variety. And I think a lot of times the kind level in those Cenozoic mammals probably at the family level. I think in some cases it's the order level with the elephants. I've done some study of the elephant types, and elephants are, I mean, that's a unique beast, and trunk and all that. And there's a lot of different elephants in the fossil record. And then we had Ice Age mastodons, gomphotheres, mammoths, and also straight-tusked elephants. So you had some variety after. But I would say that you can explain all that variety from the elephants being at the order level, above the family level.
Right.
I think the family level is an average. I think in some cases it could be genus level, but I think it averages the family. Now, this is what the baraminology people are coming out with, and I go along with that, even though I'm not I just read their articles.
Well, that's a good answer. And, I it's probably not that God's classification scheme is the same as man's way of classifying things: kingdom, phylum, class, order, family, genus, species. Whereas you're pointing out, sometimes it's order, sometimes it's family. And there appears to be a lot of morphological adaptive capabilities built into these creatures, like you're saying, the elephant archetype. So from your flood boundary model, which is a late Cenozoic flood boundary, correct, Mike?
Yes.
That built-in genetic diversity could certainly explain the diversity of life that we see today. But to have it at a KT flood boundary position, and correct me if I'm wrong, you would need unrealistic amounts, because then you need a walking whale essentially to evolve into a swimming whale, which would require more than just built-in diversity. That sounds like some real novel adaptive episodes. So, yeah.
Yeah, that's where our evolutionary friends accuse us of super evolution. Some of us, not me. Yeah, okay.
They use the term hyper evolution.
Okay, hyper evolution. Yeah, I don't believe that. I believe that we just had the created kinds, and God just built in a lot of diversity within it, and it was expressed in different environments, and it's pretty straightforward. It has nothing to do with evolution. It's just the manifestations of the genetic material already built in.
Amen. Well said. You nailed it. So this next question, I guess you've been so thorough and detailed. You kind of did answer this, but I'll get it up on screen just to honor the questions.
Okay.
Which flood model or flood boundary position best explains the extinction of marsupials on all continents except Australia?
Well, I think you do find a lot of marsupial fossils in the Cenozoic and even the Cretaceous on all the continents. So they're part of the fossil record. It's only in Australia. By the way, there's a lot of fossil marsupials in South America, which I think are from the flood. But anyway, those in Australia are unique, especially from Australia. And they appear to be in post-flood contexts. And so I've written one paper on that. I think it was just published in the latest journal, Creation, which is an online journal now. If any of you are interested in subscribing, go to creation.com and they should have directions for you. But anyway, I think they came over on log maps because some of the animals that did come from the ark, like snakes, frogs, they couldn't make a land bridge. About the only way you can get those in Australia is rafting on a log mat. And so I think that's how the marsupials came. And so a lot of them became extinct when it went from a wet climate early in the Ice Age, because the warm ocean had a lot more evaporation, even in areas that weren't glaciated. We had heavy rain in a lot of areas. And but then as you got into the Ice Age more towards the end, it dried. And so it dried tremendously in Australia, and you had massive drought, and that caused most of them to go extinct on Australia at the end of the Ice Age.
And Mike, do you know why the marsupials decided to stay in Australia? They saw the vast expanses of beautiful beaches and said, "Who'd want to leave here?" Right?
Yeah, except in the interior.
Oh well, yeah. Well, they stayed on the outskirts, but Mike, I've got a question here from Jungle Jargon. I mean, I can answer it, but you can add to it if you like. Jungle Jargon says, so what is the volume of the remaining sediment layers from the global flood? Now, I did some maths some time ago on this, and I found out that the average elevation of land above sea level is approximately 841 meters. Now,
Yeah.
if you multiply that by the total land area on Earth, you can get the total volume of the Earth above sea level. Okay, but now adding to what you presented, where 1,900 meters of sediment was eroded into the oceans, obviously that figure that I've calculated can be much greater, probably double what it is. And the reason why I actually did that is because a lot of people say to us, there's not enough water to cover the land. Well, based on my calculations, you could fit the volume of land above the sea level in the oceans 12 times. Even with the extra material that you suggested was eroded into the oceans, that's 6 times. You could literally fit all that material in the current oceans 6 times. That's a lot of water. That's a lot of volume.
Yes, and just a second. I just read this book, and he goes into those things, showing that all the volume on the continents can be eroded off in a few million years, things like that. He has all kinds of quantitative calculations that are hardcore, showing that the Earth cannot be nearly as old as they claim. Stories about Earth history. So I just got it. Just came out, and it's a short little book, and it actually goes through the calculation you were mentioning. And
yeah, Mike, I believe it was Dr. Galuli who first calculated that particular number, and he estimated that within 10 to 12 million years, with the current erosion rates of 6 centimeters per 1,000 years, it would take 10 to 12 million years to erode the current land surface down to sea level.
yeah,
And even when you consider some of the Rocky Mountains, they've increased that number to about 42 million. Even with 42 million, their scenario just doesn't work, because if that volume of material has been eroded into the oceans, why are we still finding fossils in the geological layer?
yeah, they should have eroded.
And by the way, why is there a geological layer with that amount of erosion?
Yeah, you wouldn't have it. He did. I mean, he does all the kinds of calculate erosion of North America. The erosion on the Atlantic side is more than on the Pacific side, and by the amount of erosion today, he finds out that you can erode all North America in a few million years. I mean, he goes through all, and these are really hardcore statistics. They're not really much. Should be hardly any debate about these numbers, and these are the logical things. And he goes at one after another, and I love how quantitative it is. So yes,
Well,
we have a lot
to
of
have their
evidence.
rescue devices.
Yeah, they're hard to find. I've heard of some of them, but like the land is continuing to come up as it erodes, but then the layers with all the fossils would have been eroded off long ago.
Yeah.
And we have just a bunch of igneous rocks and metamorphic rocks on the continents. So, yeah, we can go into their rescuing devices and show that they don't rescue very well.
That's a perfect way to put it. Well, this next question, I think, again, demonstrates the explanatory power of the flood boundary model you're putting forth, Mike. The question is, can you talk a little bit about how thick, pure coal seams might point to a very late Cenozoic boundary?
Well, coal say you assume that the Cenozoic is post-flood, you'd have to grow the plants, gather them and thickly, cover them up. Coal has to have a lot of overburden to compress it and heat it up, several thousand meters. And then that all gets eroded off for the coal that's at the surface. So I think I got off on a tangent, but that would be difficult after the flood. During the flood, there are probably log mats that sank or were beached when the local flood level dropped in shallow floodwaters, and they beached and it rose up and pinned it down with sand. And then you add a lot more thousands of feet, and then you compress it and heat it in coal. So that'd be our general model for forming coal in the flood. So what was precisely the question? I kind of got off on several tangents there.
No, that's good. That's good. The question is, can you talk a little bit about how thick pure coal seams might point to a very late Cenozoic boundary rather than the KT flood boundary?
Oh, yeah. Okay. Like I said, you got to go into how coal's formed. You got to heat it up to about 150 degrees centigrade, something like that. So you got to gather the plant material. You got to grow it after the flood, and then gather it into huge layers. And then you got to put several thousand meters of sediment on it. For anthracite, you need 6,000 meters to press it down, heat it up. And then if it's at the surface, it indicates that all that overburden got eroded. And this is all in the Cenozoic. So that, I'd have to say, I don't like being dogmatic. I mean, I was a weather forecaster and put out 100% chance of precip sometimes and got burned by not getting it. So I'm cautious, but I think in this case, I would say that this would be impossible after the flood to grow that vegetation, gather it together, put several thousand meters of sediment on it to compress it, heat it up, form the coal, and then erode it all off. And then where it went after it was eroded, it's not on some big floodplain nearby. It's totally taken off the continent.
Right.
So that's,
I think that's an amazing answer. And to me, that's my thinking as well, because as you're putting it so perfectly, you'd have to grow the plants all post flood, grow the plants, gather it together, and then through the necessary processes like compression, heat, pressure, create all of this coal post flood rather than in the flood.
Mm-hmm.
But just by reiterating this, I'm thinking that would be a lot of heat and pressure for the post flood environment, which I would assume would be pretty detrimental to the animals and humans as they're spreading out in all parts of the globe as well. So it seems like a multi-layered problem for the KT flood boundary position, but a very powerful reason for the very late Cenozoic boundary.
Oh yeah, I got 33 reasons. I mean, some of them are climatic, like the Cenozoic had huge volcanism. You'd have so much volcanism that you'd have volcanic winter because volcanic particles and aerosols reflect some of the sunlight back to space. You'd have a very cold Cenozoic, and yet much of the Cenozoic animals are warm climate types, even at high latitudes. So that's just that's a climatic thing, just a volcanic winter. And then we had some big meteorite impacts in the Cenozoic too that would cause impact winter. By that, it's where it reflects a lot of the sunlight back to space. You cool the land, and so that'd be one problem. So I have 33 criteria saying it's in the late Cenozoic. I'm rather surprised at these questions because I've been writing about this for years, and I have a massive amount of material out. But the more speculative questions are about where the pre-flood flood boundary is, whether we had the big switch, and some of that stuff I said towards the end that I thought would be more controversial. And
Interesting, eh? Yeah. I guess this ongoing debate on the flood boundary is just controversial to the point where the questions keep coming up. It's ongoing. I'm sorry, George. I know you're going to say something. Go ahead.
Oh, I was just going to add that I wrote an email, Mike, to the big three, ICR, CMI, and Answers in Genesis, effectively saying that, you write fantastic papers and articles on various aspects of the debate of evolution versus creation.
Mm-hmm.
But you have to remember the skeptics won't go to these websites to read what we write. So that's why I suggested make more of your scientists available for debates or presentations at a platform where these skeptics actually come to listen to the arguments. Because I guarantee you, they won't go to the ICR, CMI, Answers Genesis website. Not very many of them, but some of them do. And they call themselves critical thinkers, yet they won't read the information.
Yeah,
that
they
sort
don't.
of gives them a different opinion of the data or the evidence that they find.
Yeah, they usually bring up a lot of straw man arguments for what we believe. Yeah, we're a lot more sophisticated than any of them can imagine. They need to read our material first.
Right.
To be scholarly, you need to look at someone you disagree with. You need to look at his data and his reasoning and his evidence. And a lot of times they don't do that. And the reason I know that is because I read their books and I look at their references. And they hardly have any of our material, and that they do, it's an old book, like the Genesis Flood, that's got some good stuff in it still, but it's needs to be updated. So they have stuff like that. So a lot of straw man arguments. So if you're a skeptic out there, please be scholarly and examine our arguments first before you criticize us. And we have things we need to explain still, and I freely admit that we have a lot of explaining to do in our science still, even though I believe we have the big picture of the flood. We're looking at the details, which can be difficult to explain, and we'd appreciate it if you really wanted to get into them, to at least educate yourself on what we say first.
Amen.
Yeah,
well
Mike.
said, Mike. And I think that's why your arguments, your articles, your papers are so powerful and just filled with so much good information, because you're looking at both sides. As you've explained many times, you spend a lot of time in these secular journals, and you're finding a lot of major problems with the secular models in terms of
I read their material and digest it. And I read CPT stuff, catastrophic plate tectonic stuff. I read anything and everything. I believe in 1 Thessalonians 5:21. Examine everything carefully. Hold fast to that which is good.
Amen.
Yes.
Amen. So I'm just going to get right.
You'll also find, Donnie, that you and I have experienced this. They'll even quote you secular papers, and you know that they've never read them completely. They've read the title and the abstract, but never really the details of the paper.
Mm-hmm.
Because when you read the details of the paper, it completely changes your perception of what the abstract was actually saying. So that's another aspect of their thinking skills just aren't there. Don't just read the title of the abstract, guys. Read the rest of the paper. See what they're actually saying.
Yeah.
And a good example of that was the scales to feathers. It's not until you get into the details of it that you find there was nothing like proof that scales were evolved to feathers. Nothing like it.
Yeah, I agree with you there.
Yeah.
Well, I noticed that personally with a book I recently published a few months ago, the Endogenous Retrovirus Handbook that I have right here, where I spend 95% of it going into the secular literature when it comes to endogenous retroviruses and pseudogenes and a lot of these genetics-based arguments. And, the explanations for what we see in terms of these functional DNA elements, unfortunately, the skeptics aren't critically thinking about those explanations. Are these empirical? Are these legit, or as you gentlemen have put it, are these just rescue devices? So very good points. And I wanted to get this question in here as we time, as always, Mike, just flies by with you. A lot of compliments in the chat. We've had a big chat, and as you know, a lot of questions. So we'll kind of start winding it down here. I do want to respect your time. So this question pertains to what we've been talking about, and those that would hold to, I guess, a KT boundary flood model, if they were to look to the iridium layer, with what you're saying, the meteor impacts during the flood itself, the impact theory, as well as the you were just talking about the worldwide volcanic activity and these winter
volcanic winter or nuclear or impact winter. There's also nuclear winter from a nuclear war also.
Right. So the impact winter or volcanic winter, would that, from an upper, a very late Cenozoic boundary, would that explain possibly what we see in terms of the iridium?
The iridium, yeah, I've thought a lot about that. I think if they really measured the sediments for iridium, they'd find a lot of iridium layers. But they always look for them around the KT boundary, and then sometimes they're not there. Sometimes they have to add them from above and put the KT boundary up. So, and the original one they found in Gubbio, I think is how you pronounce it, Italy, in 1980, that supposedly verified the impact hypothesis for the KT boundary and the extinction of the dinosaurs. That was supposed to be an iridium spike, but a later paper said that the iridium was spread out over 4 meters. So I think there's a lot of, if you go into this data in detail, I think you're going to find a lot of glitches, and I think a lot more iridium layers are out there, because I think there's a lot of impacts during the flood that would cause high iridium in certain layers. So
very good. Very good. Okay, let's kind of wrap it up here. I'll get let's see here, question wise, something that's really on topic. Okay, here's one that comes in from Ken Rock. Appreciate it. So he asks, question for Mike: how would a worldwide flood not kill all the sea life? You would have the mixing of salt and fresh water, increased water pressure from the extra water, and its increased height.
Well, first of all, it did kill a lot of sea life.
Right.
Yeah.
But we don't expect it to be chaotic and turbulent everywhere at all times in the early flood. So there's going to be a lot of pockets in the flood waters where the water is not so salty or towards the fresh. And by the way, the pre-flood ocean probably was much less salty than the current oceans, because a lot of that salt of the current ocean is a result of the flood breaking up sediments and the dissolved chemicals ending up in the ocean. So, and also for as far as there'd be hot areas near impact craters, the water would probably be very hot, but away from it, it wouldn't be. And so you had quite a lot of mixtures. So a lot of the sea creatures can survive in those refuges, as they call it in Ice Age geology, where some animals survived various ice ages. And some mountain peak in Sweden, for instance, they have refuges for them. I think there's a lot of problems, but anyway, I'll use their terminology, and so there'd be a lot of places where they can survive. But we know that massive amount died. In fact, the most fossils are marine, but 95% or more are marine fossils.
Yeah, correct.
And there's probably hundreds of billions of fossils, if not trillions. And so, say at 1 trillion, so we know that maybe 1 trillion died. And so Yeah, we had a lot of death of sea creatures in the flood, but we'd have a lot of that would survive in favorable areas.
Appreciate the answer, Mike. I'm going to get one last question in here since it came in the form of a donation. A lot of people, a lot of compliments from the chat, Mike, saying that this was very informative and they really enjoy these live interactions. So they're very helpful for the community. So here's the last one. This one comes from Samir. I appreciate the support, and we'll make this the last question, and we're going to wrap it up at the 2.5 hour mark. So, Mike, I do appreciate your time. Okay. So Samir asks, why are atheist astronomers willing to accept that dry Mars was once completely covered with water, yet they mock the idea of a flood on a 73% water planet?
Yeah, that's a good question. And in fact, I just got through studying the floods on Mars and Mars itself. I wrote 3-part paper that's being reviewed by the Creation Research Society Quarterly, and it was my topic at the CRS conference this late July at Liberty University. And I've always wondered about the floods of Mars, because when you look at those floods on a planet that's cold and dry, they have a lot of problems explaining them, and some of them were huge floods. Mainly one. The rest of them were not nearly as big as Cassie, K-A-S-I-E, Valles, V-A-L-L-E-S, Cassie Valley, of which they had channel scabland features like from the Missoula Flood in eastern Washington, which I've written about and I have a DVD on. And I thought to myself, wow, and they're huge. They indicate 10 to 100 times the volume of water in the Lake Missoula Flood. If you know anything about the Lake Missoula Flood, a lake in western Montana, 2,000 feet deep, burst through the ice at the peak of the ice age and flowed over Spokane, Washington, 600 feet deep, and carved up eastern Washington into what's called the channeled scablands. And it had streamlined silt hills and features. And you see these things on Mars in these outflow channels. And anyway, to make a long story short, as I delved into this, I found out that that these floods, and also a group of other floods, smaller floods called valley networks, they can be accounted for, I believe, by impacts, because based on the decay of the magnetic field of Mars, some of the large impacts were when the field was almost gone. And Russell Humphreys done some calculation, and the half-life of the Mars magnetic field from creation is 308 years. So after about 1,600 years, you don't have a lot of magnetism left. And so these impacts destroyed the magnetism, and only a little bit came back, which would place it right in the flood. So I believe impacts, which were a big part of the Genesis flood, also were a big part of the floods on Mars. Impacts plus volcanism caused the water, the warm temperatures, the flooding. So I think it all fits together during the Genesis flood, at the time of the flood. And you're right. I think we can account for the floods on Mars now, when they have serious problems accounting for them with it's a frozen, dry landscape. And well, we have 73% of the planet is water. I mean, yeah.
And Mike, this is their words, not ours. With regards to the size of the canyons on Mars, they call them canyons of biblical proportions.
Yes,
and yet they'll deny the flood on Earth.
Yes, there's some very deep canyons like Valles Marineris. That's 10 kilometers deep, 4,000 kilometers long, 300 kilometers wide. It's a series of canyons all connected.
Yeah.
And I think they have a place in the outflow channels where there was a huge lake that developed in that big canyon that burst first onto the ground and then up and formed these huge floods. Anyway, that's all part of my paper. In fact, I have so much good material on Mars. I think I'm going to write a book this winter about it.
Yeah, you might as well just add to the library, Mike.
Yeah, I mean, I feel motivated to not only do in-depth research, but get the information out for the lay people. This would be a layman's book. So it can bless them, and they, because I found on Mars, there's so many things they can't explain besides the floods that we can explain. And not only that, I found indications of young age, several of them, and there's even more that I can do research on. So anyway, some of those are published in this 3-part, not published, but under review, in this 3-part paper on the floods of Mars. So a lot more information on this. So anyway, that gave me material for another book. I feel compelled to get the material out to bless people. That's my goal.
Amen, Mike. Well, you've been a huge blessing, and I can say I've spent hours and hours and hours reading through your material, your books that I have, behind me and in my library upstairs, as well as all your number of articles. So, again, I do appreciate. I know how busy you are with all the research you're doing, the articles you're publishing, the book. So, I always appreciate, and the audience does as well, the time that you give to us. Especially during the discussion portions after your presentations. Lots of good questions come in, and you always give very thorough and informative answers. So God bless you, Mike. I do want to hand it over to you, though, if you had any final words, final thoughts, as we close it down at the 2.5-hour mark. So,
well, for creation scientists, Christians, old Earth Christians, theistic evolutionists, atheists, I just encourage you to read what we've done in 60 years. I and many others have provided some great in-depth stuff. We write stuff for laymen and children. So please avail yourself of this and be open-minded to see if what our case. We have a case that Genesis 1-11 is real history, in which case we can believe Genesis 1-11 is real history, and I believe the evidence overwhelmingly supports that. We can easily believe the spiritual parts of the Bible that tell us how to get to heaven, and what we and how to live on earth. So
Amen.
That's what I'd like to leave the audience. And thank you for listening.
My pleasure. Yes. Great final words. Very important. It's not about winning arguments. It's about winning souls. And the Bible tells us how to live here on this earth and how to get to heaven, brother. Well said. Well said. George, final words?
I agree with Mike's sentiments there. Just an apology to Alec Cox. I'm afraid I didn't see his question, so I'm not sure whether you did either, Stanley. That's probably why we didn't ask it. So sorry about that, Alec, but I'll leave you with this. I always try and add a bit of scripture as well. But may the Spirit of God open your eyes to the light, your ears to the truth, and your heart to his Son, the Lord Jesus Christ.
Amen.
Bless you all.
Amen.
God bless you as well. Thank you again, George, for being here as co-host. Thank you, Mike, for giving us your time. And to the audience, thank you so much for being so engaged in this important topic. And there's nothing more important than origins and where we're going to spend eternity. So, and again, the chat was just really lively and flying by tonight. So I did miss some questions, and I do apologize for that. But I do look forward to having Mike on again in the future for a 9th time. So with that being said,
Donnie, with these kind of presentations with so much data, I usually watch them 2 or 3 times to absorb all of it. So, Mike, thanks very much. I'm gonna go through 2.5 times 3 hours. What's that? 7.5 hours. Thank you.
Okay. I'm the same way, brother.
Great information, mate. Fantastic.
It gives me something to do. Okay, here we go. Standing for Truth is out. Thanks again, all. God bless.